Hello there. Welcome to Chemistry Chapter 2, Lecture 1. In this lecture, we're going to be covering on your own problems 2.1 through 2.5. And in your textbook, we're on page 37. We're going to go through page 50. And before I get started, I just want to thank you for watching. And please like, comment, and subscribe. And you can support my channel with a small donation. There's a link in the description box, or you can scan this QR code. All right, let's get to it. You'll need your Chapter 2 notes, a calculator, and your textbook. Okay, so let's talk about the notes for just a second before we start working any problems. So this chapter is basically about energy. So energy is the ability to do work. And when we talk about work from a science standpoint, we are talking about causing motion. So work is force times distance. So you've got to have movement over a distance in order to have any work. So work is a concept that we talk about a lot in physics. All right, just introduce it to you here in chemistry. Now, the first law of thermodynamics, it's a famous scientific law. Energy cannot be created or destroyed. It can only change form. So an example, just a very simple example, is if you rub your hands together, right, your hands over time will start to get a little hot. So the energy of motion moving back and forth ends up changing to the energy of heat, all right, because the friction causes heat. So that's just changing the form of energy. The energy isn't destroyed, it's just changing form. So the amount of energy in the universe is finite, and you've got your famous Einsteinian equation equals mc squared there. If you take physics, you'll talk about that a lot more. So we have potential energy is stored energy. And in order to have stored energy, you must have mass. Kinetic energy is energy in motion. All right, so if I were in the classroom, I would do a couple of examples, and maybe your teacher will do some examples. We did some examples with methane gas and with potassium permanganate solution. And hopefully your teacher will show you a couple of cool demos there to show the changing of energy from one form to another. So energy is measured by the unit joule. All right, so a joule is the energy required to move a 102-gram object 1 meter. Now, when we talk about energy, a lot of times we talk about temperature. So with temperature, you do need to memorize a few important points here. So, for example, Fahrenheit, you probably know that water's freezing point is 32 degrees. And the boiling point is 212 degrees. And with Celsius, with the water's freezing point is 0, and the boiling point is 100. Now we're going to introduce another scale. This scale is called Kelvin. All right, so Kelvin is really related to the Celsius scale, but it can never go negative, whereas you know Celsius and Fahrenheit can both go negative. Kelvin is what we call an absolute value scale. All right, so Kelvin, the water's freezing point is 273.15 and its boiling point is 373.15. So you can see that it's 100 degrees greater in Kelvin. So it just kind of follows the Celsius scale. So negative 273.15 is the absolute absence of heat for the Celsius scale. And so 0 Kelvin means the absolute absence of heat. Okay, so this, you've got to memorize this equation that Kelvin is the degrees Celsius plus 273.15. So you really need to memorize all of these temperature conversion equations for the test. That Celsius is 5/9 times Fahrenheit minus 32. Fahrenheit is 9/5 times whatever the Celsius temperature is plus 32. And then Kelvin is whatever Celsius is plus 273.15. So let's do some of these conversion examples. So open up in your book to page 46. We're going to do on your own 2.1 on page 46. So that one says normal body temperature is 98.6 degrees Fahrenheit. What is this temperature in Celsius? Okay, so looking at your temperature formulas, you're going to use degrees Celsius is equal to 5/9 times Fahrenheit minus 32. All right, and so degrees Celsius would be 5/9. Fahrenheit is 98.6 and minus 32. So let me show you the way to put this in your calculator without making an error. So we're going to want to put that 5/9 fraction in parentheses. So do a left parenthesis, 5 divided by 9, and then a right parenthesis, and then times left parenthesis 98.6 minus 32, and then close the parenthesis there. And hit enter, and you've got 37 degrees C, or Celsius. All right, let's do another one on your own 2.2. Okay, we'll read through that one real quick. So we have, if water boils at 100 degrees C, what is the boiling temperature of water in Fahrenheit? Okay, so this time we're solving for Fahrenheit. So degrees Fahrenheit, looking at that equation, it's 9/5 times the Celsius temperature plus 32. All right, so we were given that it's 100 degrees C. So Fahrenheit's going to be 9/5 times 100 plus 32. All right, let's put this in our calculator together. So we're going to put that 9/5 in parentheses. All right, otherwise it's going to make a mistake. So times 100 and then plus 32. So that's 212, and you already know that that's the right answer from the table in the notes. All right, so remember, it's going to multiply first in your calculator and then add the 32. So if you don't put the fraction in parentheses, your order of operations will get off, and you'll have it'll give you the wrong answer. All right, let's look at 2.3 on page 47. So this one requires 2 steps. So it says, what's the Fahrenheit equivalent of 0 Kelvin? So we don't have an equation that goes directly from Fahrenheit to Kelvin or Kelvin to Fahrenheit. So we need to convert to Celsius first, and then we'll convert to Fahrenheit. So we know that Kelvin is equal to our degrees Celsius plus 273.15. So if we want to know what's the degrees Celsius if Kelvin is 0. So we're going to plug 0 in for Kelvin. So I'm going to subtract 273.15 from both sides of the equation. And I would have negative 273.15 is equal to Celsius. So now I can convert that to Fahrenheit because we know Fahrenheit is equal to 9/5 times the temperature in Celsius plus 32. So that's going to be 9/5 times negative 273.15 plus 32. Okay, let's get this in our calculator. Try not to make a mistake here. All right, we're going to put that 9/5, 9 divided by 5 in parentheses, times negative 273.15. Now, I don't have to put the negative 273.15 in parentheses, and then plus 32. All right, and we get negative 459.67 degrees. So that is as cold as you can possibly get. In fact, that's the complete absence of heat. And that is not a temperature that has been achieved in the universe. Even deep space is about 3 Kelvin. Okay, so very, very, very cold, but not the complete absence of heat. Although that temperature has been attempted to get to in labs, but they just haven't quite made it. And you can read about that in your reading between page 37 and 50. All right, let's talk about a few other terms. Calorie, you've probably heard about that because on all your food containers you see calories labeled. It's the amount of heat. So calorie is just a heat measurement. It's the amount of heat required to raise 1 gram of water 1 degree Celsius. Now, you're going to need to do a conversion of calories to joules in your homework in practice problem number 4. So just you need to learn that conversion. And you'll learn it quite a bit as we work some of the problems. Now, in measuring heat, we have an equation, Q is equal to mc delta T, where Q is equal to the heat released or absorbed, and that is in joules. M is the mass, that's going to be in grams. C is specific heat, I'll talk about that in a minute. And then delta T means change. So delta T is the change in temperature, and it's the final temperature minus the initial temperature. So if something's being heated up or cooling off, it's the final temperature minus the initial temperature. Now, specific heat is a measurement of how easy it is to heat up an object. So, for example, we've got metal versus plastic versus styrofoam. You know, if you set all 3 of these materials out in the sun, the metal's going to heat up really hot, right? Plastic will heat up some, but not too bad. You can probably pick it up after a while on a hot summer day, but it's going to heat up some, but nothing like metal. And then styrofoam will hardly heat up at all. That's why we use styrofoam in coolers, all right, just to keep our drinks cold, right? So this is really important. The lower the specific heat value, the easier it is to heat up an object. Okay, so let's talk about that for a second. So if you'll open up to page 50, right, we can talk about these two on your own problems. So 2.4 says, and we're going to be referring to this table, all right? So 2.4 says, what substance takes the least energy to heat up, copper or glass? All right, well, the answer is copper. Copper has a lower specific heat than glass. It's about half as much. Okay, so that means it takes twice the energy to heat up glass the same amount as copper. Okay, so the answer to 2.4, we'll write this in your note. Easier to heat up is copper. All right, and then on your own 2.5, of course both of these are on page 50. All right, 2.5, you'll read along. It says a copper kettle and an iron kettle are placed side by side on a fire. After 3 minutes on the fire, the iron kettle reaches a temperature of 100 degrees. Will the copper kettle's temperature be higher or lower than 100 degrees? Okay, so we can see that copper is a bit easier to heat up than iron. It has a lower specific heat value. It's not a lot lower, but it is lower. So if it took 3 minutes to heat the kettle up to 100 degrees, okay, and you put a copper kettle on for the same amount of time, since it's easier to heat up, the copper kettle will be higher than 100 degrees. All right. So the temperature will be, so the temperature of the copper kettle will be greater than 100 degrees Celsius, right? Because copper has a lower specific heat than iron. That makes it easier to heat up. All right. So the homework that goes with this lecture is the review questions, and this would be on page 67, 1 through 8. Now you will have to do some reading in that 37 to 50 and those page ranges to get some of these review questions. They're not all in your notes. And then the practice problems on page 68, 1 through 4. And remember, on practice problem number 4, you'll need to make a conversion from a conversion from calories to joules, or vice versa. In fact, let's open up to that one, because in the past I've had students be a little confused about practice problem number 4. So let's talk about it. So it starts with 2,500 big C calories, okay? How many joules is that? And so we're going to want to convert from big C calories to little c calories, and then convert that to joules, knowing that little c calories, 1 food calorie, which is big C calories, 1,000 chemistry calories, and then a chemistry calorie, that's little c, is 4.184 joules. So just be careful with that one. That one will be number 4. That will be 3 sets of parentheses to go from big C calories to little c calories and then to joules on that. Okay, so that's just a unit conversion problem, just like in chapter 1. All right, so that's it for this video. Again, please, you can like, subscribe, support my channel. I think I'm going to finish this video. I've got a new microphone. We're going to test it out just with a little bit of guitar in the key of E. And I hope you have a great day.